All right, so to pick up where we were talking about valence electrons and drawing those diagrams, the other thing that's going to be important for when we eventually get to bonding after break is the idea of this octet rule. And again, I know this is something that you've talked about before, and a lot of you have used similar explanations to it to talk about the metal reactivity and ion formation in the lab. But we want to talk a little bit about more what that is and more importantly, why that exists. And that's going to come down to the balance of Coulombic forces as we've been going through the last couple weeks here. So first and foremost, the octet rule refers to the fact that based on experimental evidence, when chemicals react, they tend to do so in a way and bond in a way that allows them to have an octet for their valence electrons, meaning that they're going to gain or lose or share electrons until they reach 8, right? Hence where the prefix oct is coming from, 8 valence electrons. Now this comes down to the balance of those Coulombic forces that are at work in the atom. And as a result, there are some exceptions to them. These are generally the exceptions that we're going to run into here. But as an example of why one of these exceptions exists, if we look at lithium really quick with its Bohr model. Lithium has 3 protons and 3 electrons with a Bohr model that looks something like this. Now we know that this arrangement exists because the protons are pulling on the electrons around them, right, keeping them into the atom. But as we go to the second energy level, that attraction pulling in is a little bit weaker. Now for lithium here to reach an octet of 8 electrons, that means it would need to gain another 7 electrons on this outer shell. Now lithium already had a weak attraction for its 1 electron, which means that as we start adding more and more electrons onto the shell, we're going to increase all of the repulsion in this atom without increasing that attraction anymore. Lithium could barely hold on to its 1 electron. It's definitely not going to be able to hold on to 7 other extra electrons and all the repulsion that they bring. So lithium is one of those atoms that does not go to an octet. It's stable with just 2 electrons after losing that one that it had a weak attraction for. In general, this brings us to an overall rule that metals tend to lose electrons, which we've already talked about from the reactivity lab. Nonmetals, on the other hand, will gain them. And this is because nonmetals, being on the right side of the periodic table, have a really large number of protons for their period and have a really strong attraction, and they can overpower that extra repulsion. And then our metalloids, which was that zigzag band in between them that we haven't really talked much about up to this point, they have an attractive force that's somewhere in between, so generally they can gain or they can lose. It just depends on what they are paired up with. So using this octet rule and this idea that metals lose electrons, nonmetals gain them, and metalloids can do either, we get to what are called oxidation states. Oxidation states refer to the charges. It's the technical name for the +1, +2, +3, etc. charge that different metals or nonmetals can form. So we get that by looking at their electron configurations and specifically what's going on with the valence electrons, because they're going to generally react in a way that gets them to 8 valence electrons. If we take our simplest one to start off with, for potassium, its highest energy level here is energy level 4, and it has 1 valence electron. So if it is going to reach a stable octet, there's 2 options. It could lose this 1 electron here, which would get it an octet at the 3 energy level. Alternatively, it could gain 7 to reach an octet at the 4th energy level. Now, potassium, again, has only 1 electron in it. It's the very first one in its period over here. And we know from our reactivity lab and from ionization energy that it has a fairly weak attraction for that 1 energy level, for that 1 electron, because it only has 19 protons. As a result, the amount of repulsion that would occur by adding 7 more electrons is way too much that the potassium cannot hold on to all of them. So as a result, it takes less energy to lose this 1 electron and rip it away than it does to force 7 more electrons onto it. And again, since potassium is a metal, this follows that pattern that metals are going to lose electrons. So if it loses that 1 electron, its oxidation state is going to be +1. And since we know that every single element in a group shares the same ending electron configuration, That tells us that all of these elements will make a +1 cation. For calcium, if we apply the same thinking, calcium is also a metal. Everything else in group 2 is also a metal. It's going to require less energy to remove these 2 electrons than to gain 6 more. So these ones will all form a 2+ cation. We're going to skip across the D block right now because the D block we know is at a lower energy level than the outermost. So in terms of how they lose electrons and the ions they form, it's a little bit more complicated, and we're going to deal with that after the break. Jumping all the way across to group 13 with gallium, looking at the highest energy level of energy level 4, we see that it has 3 valence electrons. And being that gallium is a metal, right, as indicated by this section here, right, all of these elements are metals. It's going to also lose its electrons, or its valence electrons, which means it's going to get a +3 charge. So all of the metals in this column will get a +3 charge. For a metalloid, we know that its charge is, its attractive force is somewhere in between that of a metal and a nonmetal. So for boron here, it could lose those 3 electrons, or it can gain some because it has that in-between level of attraction. So it could alternatively gain the electrons it needs to reach the octet, the second energy level. If we continue looking at the pattern going across, germanium and arsenic. Now what's different here is if we look at our periodic table, germanium and arsenic, those are both metalloids. So just like boron, they can gain or they can lose electrons for either one of these. So germanium currently has 4 valence electrons, so it could lose all 4, or it can gain 4 more to reach its octet. Arsenic has a total of 5 valence electrons, so it can lose all 5, or it can gain 3 more. And then after that, we are into our nonmetals, selenium, bromine, and krypton. Now, unlike our metals, these ones are not going to lose their electrons again because of those Coulombic forces. We see that now we're up to 34 protons, which is a really big increase from potassium's 19. It's such a bigger increase that it's going to be really hard and require a tremendous amount of energy to remove all 6 of these electrons at this point. And because it has so much attraction, it can easily compensate for the extra repulsion of adding just 2 more in. So what this means is that it's going to gain those 2 electrons, which is going to give it an overall -2 charge. Likewise for bromine, with its 7 valence electrons, it has a really, really high attractive force due to its 35 protons, so it's going to easily gain 1 electron to become a 1- ion. Krypton, over here at our noble gas, krypton has 8 valence electrons, so it does not need to do anything to reach a stable octet. In fact, it doesn't gain any electrons because if we needed to gain an electron, it would have to go up to the 5th energy level, and that means that we're going to be going even further away from the nucleus, and that attractive force would get weaker. So it's not strong enough to overcome that extra gain of an energy level to hold on to that extra electron. So it's not going to gain anything because it's too weak. And it's also not going to lose any of the 8 that it has because it is extremely strong for the amount of energy levels that it has. Right? So as a result, the noble gases, they don't tend to react. They don't gain, they don't lose because they're not strong enough to pull in another electron, and yet they are too strong that they can't lose their electrons.